Hello everyone. In this video lecture, we are going to learn about integer linear programming problem. So let's begin. Before we start, we should already be familiar with what do we mean by a linear programming problem, also known as LPP. So in a linear programming problem, we are given the objective function maximize or minimize z equals to c transpose x, where this c is the cost vector, x is the unknown vector, and these are the constraints ax equals to b, and this is the non-negativity restrictions, x is not negative. Now if I give you an additional condition that x has to be integer valued, then the problem is said to be ILP. So we have the definition that a linear programming problem is said to be an integer linear programming problem if some or all decision variables are restricted to take integer values. So the important word here is some or all. So if all of them are supposed to be integers, then we call a problem pure ILP. Otherwise, if few of them can be integers and few of them can be non-integers, we call the problem mixed ILP. But you will learn through this video lecture that the techniques of solving both kind of problems, pure and mixed, are same. So to understand the solution technique, let's have a look at how does a feasible region of a linear programming problem looks like. So I've taken the example of two variables so that graphically we can see the feasible region. So I've taken a hypothetical example in which I have drawn these two constraints, and this is the shaded region which I am assuming to be my bounded feasible region. It has four corner points A, B, C, D. But if you talk about how many solutions are there, how many feasible solutions are there, so the answer is infinitely many, because the variables x1, x2 can take continuous values. So what changes it will bring if I restrict my variable x1, x2 to be integers? So since now only these red dots will be the feasible solutions, because x1, x2 can take discrete integer values 0, 1, 2, 3, 4, 5 and so on. So therefore these are the finite number of feasible solutions I will be getting in a bounded feasible region ABCD. So what do we think we are going to do with these finitely many solutions? We're actually going to find the optimal solution out of these all finitely many feasible solutions. But it's difficult, it's computationally expensive to compute first all the integer valued finitely many solutions and then pick up the best solution. So therefore there's a better technique to do that, and that technique which we are going to introduce is branch and bound technique, which is specifically used to solve integer linear programming problem. So in this video lecture, our focus is only on two variable problems because the solutions can be seen graphically. However, the technique is very general and can also be applied to problems having more than two variables. So this is the example. I'll be explaining you branch and bound technique by applying on an example. So I have considered two variable problem in which my restriction is given x1, x2 are supposed to be non-negative integers. So that's a pure integer linear programming problem. Okay, so let's learn what to do. So what should be the first step of branch and bound technique? The first step is you just ignore the integer restriction. That means you relax your problem, you relax the condition of variables being integers. So this problem is called relaxed problem, and you solve it. Solve it means you find the optimal solution of the relaxed problem. And since it's a two variable problem, so we can find the optimal solution graphically. So let's do that first. So there is a appropriate representation of branch and bound technique solutions. We draw a tree-like structure in which the first node, in which at every node we write the optimal solution of the different LPP. So this is my LPP1. The relaxed problem without integer restriction is the LPP1. So I'll be writing in this box the optimal solution of the relaxed problem. So let's find the optimal solution of the relaxed problem. So I have drawn the feasible region, and this is bounded by A, B, C, D. And although I have also drawn the red dots depicting the integer solutions, but right now I'm interested in the solution of the relaxed problem, and we all can very easily figure out by substituting the value of a, b, c, d in the objective function that c is going to be the optimal solution, and the coordinates of c are this 3.75 and 1.25. So once you get the optimal solution of this problem, you write it here in that box. So we have done the first step, we have computed the solution of relaxed LPP. So now, if the solution at this stage is turning out to be the desired one, so what is the desired solution? We want integer solution. So if both x1 x2 are turning out to be integers, then you stop there. The same solution will go as the optimal solution. But if both of them are not integers as it is required in the question, so that means this is not the desired solution. We need to continue the question. So now we need to know what to do in continuation. But before that, we need to look at this z value. So this z value actually acts as an upper bound. It's a maximization problem, remember. So what do we mean by upper bound of z? It will be clear to you soon when I'll be explaining you the next step. The meaning of upper bound is that you cannot get a better z when you proceed in the question further. That means for a maximization problem, this is the maximum value of z you can get. So nowhere you will be getting a solution which will give you z greater than 23.75. So that's why this is an upper bound of the value of the objective function. So we may get 23, we may get 22, we may get 21, 20 and so on, but we can never get 24, 25. So this is the upper bound of z. So what to do now? So this is a non-integer solution. So we need to do the next step. And what is the next step? The process is called branching. As it's clear from the name, it's branch and bound. The meaning of bound I have just explained to you. It is an upper bound. But what is branching and how to do this branching? So we need to know that. So actually branching means we have to choose one of these variables for the branching. So that's the question we are looking an answer for, how to do branching. So we have to choose that variable for branching which is having non-integer value. And since here both of them are non-integer values, x1 and x2, so we will be choosing any one of them. It's completely arbitrary. So choose x1 as your branching variable. So now the question is how to do branching. So x1 is 3.75 is this value. x1 is 3.75. So that means strictly between 3 and 4 we are not going to get the optimal solution because they all are non-integers. So either our solution will be lying on the left of this side less than equals to 3, or our solution will be lying on this side greater than equals to 4, because strictly between 3 and 4 all the values are non-integer. So you focus on the magnitude 3.75 and then you look for the nearest possible two integers. So you get the two branches, x1 less than equals to 3, x1 greater than equals to 4. So actually these branches mean we are adding two constraints to the original LPP, but both these constraints are not simultaneously added, they are added one by one. So this gives rise to two further LPPs, LPP2 and LPP3. So now we have to solve these individual LPPs and then look at the solutions. So what does this branching means? This means addition of constraint, and branching always worsens the value of z. So that's what I was explaining in the beginning when I was explaining you that this z is the upper bound. So that's the maximum possible value of z you have got for a maximization problem. Means at every node, LPP2, LPP3 and even the further nodes if we will be solving, we cannot get z greater than 23.75. So branching always worsens. Worsens is a general word. For a maximization problem, it means it reduces the value of z. For a minimization problem, it means it increases the value of z. Right now we are solving a maximization problem, so that means with branching our z is going to decrease. Okay, so now let's apply these constraints one by one. So firstly we are focusing on LPP2. So you draw the line x1 equals to 3 and you mark the region which is coming from x1 less than equals to 3. So that will be clearly lying left of the line x1 equals to 3. and then you find the intersection of this region introduced with the original LPP region. So original region is ABCD. So when you introduce this constraint and find the intersection of this with the original LPP, so you will see that the AGED is a feasible region of LPP2, and similarly you draw the other constraint x1 equals to 4, and since this is greater than equals to, so actually the region will be lying on right side of it. So this region should be taken intersection with the original LPP will give you this feasible region HBF of LPP3. Because now we are to solve the new LPPs, LPP2 and LPP3, so we need to identify their feasible regions accurately. So this is how the feasible regions are identified. They're actually coming from the original feasible region, but there will be a gap created between them because the region between 3 and 4 has been discarded. We have created 2 sub-regions out of the original feasible region. So now the point is you have to now find the optimal solution of LPP2. So focus on LPP2. You will see that E is going to be the optimal solution. See, you just have to track the original optimal solution. The original optimal solution was C. So when you will go to the feasible region of LPP2, this region I am talking about, so your optimal will travel from C to E. So just track on which line you are moving. So you are moving on the line x1 plus x2 equals to 5, and at E your x1 is 3. So you put this x1 equals to 3 here, you will get x2 equals to 2. So the coordinates of E are easy to compute. So you get your optimal solution of LPP2, which is giving you z equals to 23. And since that is an integer valued solution, both x1 x2 are integers, so this node is fathomed. So the meaning of fathomed node is stopping, that this node cannot have further branches. So this is one way of stopping. Whenever at any node you get an integer solution, you stop there, and it is called fathomed node. So we have got from 23.75 we have got to 23. See, I told you the value of z is going to decrease, it's never going to increase. And now we are going to do the same for LPP3. So the LPP3 feasible region is HBF. So this time C will go to this point F. So F will be the new optimal solution of LPP3, and you can very easily find the coordinates of F. This is turning out to be 4,0.83. So this is the optimal solution of LPP3. It is not turning out to be an integer solution. This is a non-integer solution. So ideally we need to continue the branching further. But whenever we are getting a non-integer solution, then we have to think something that whether there is any benefit of doing further branching or not, keeping in mind the fact that we know that with branching the value of z is going to decrease in a maximization problem. So see, you are getting here 23.33. If you choose to do the further branching, then the z which you will be obtaining will be either 23, 22, 21 and less. It can be less. It can never be 24. So maximum possible it can be 23, and you have already obtained an integer solution which is giving you z equals to 23. So that means there is no benefit of doing the branching further, as it cannot give us a better value of z than 23. So the question will stop there only. We'll be declaring this node as fathomed node because the further branching cannot improve z. So this node is called also declared fathomed, and when all the nodes are declared fathomed, the question finishes, and then we just look at all the integer solutions obtained. So we have just one integer solutions obtained, so that is declared as the optimal solution. So we got the optimal solution here. X1 is 3, as x2 is 2, z is 23. So that ends the first example, and that was an easy example because we just did branching one time. So let's understand the process of branching again with another example. So this time I have taken a minimization problem, and if you follow the same steps, the first step is you forget the integer restriction and draw the feasible region and find the optimal solution of relaxed problem. So this time I am getting unbounded feasible region. and it's easy to find that point B is going to be the optimal solution. So this is the optimal solution of LPP1. Again, both x1 x2 are supposed to be integers, but both are turning out to be non-integers, so I have to do the branching. So in this case, this is a lower bound of z because it's a minimization problem. That means with every step of branching further, my z is going to increase. So this is a lower bound of z. So I'm choosing again x1 as the branching variable. So since x1 is 0.2, so it will create two branches like this. Either x1 will be less than equal to 0 or it will be greater than equal to 1 because 0.2 lies between 0 and 1. So let's first look at what will happen if x1 less than equals to 0. So since x1 less than equals to 0 means x1 exactly equal to 0 because we are actually having non-negativity restriction. So x1 cannot be negative, it cannot be strictly negative. So if there has to be intersection between the first quadrant and the second quadrant, or you can say between the positive side and the negative side, then the intersection is just exactly at the equality. So x1 has to be 0. So since x1 equals to 0 is the y-axis, so this is the region shown from here. This from point C upwards is the feasible region of LPP2. So feasible region of LPP2 is turning out to be just a ray starting from point C upwards because x1 is having fixed value, x1 equals to 0 and y-axis is actually x1 equals to 0. So if you want to find the optimal solution of this, so since the problem is minimization and going in this direction, upward direction, z is obviously going to increase. So therefore C is the point of optimal solution here. So we get our C coordinates are x1 is 0, x2 is 2.5, z equals to 10. I told you 9.8, it is 10 now. So we got optimal solution of LPP2. This is not integer valued, so obviously we need to do the further branching. But let's first solve LPP3. Instead of doing branching here, firstly we need to solve LPP3. So LPP3 is x1 greater than equals to 1. So this is the line x1 equals to 1. Greater than equals to 1 means the original LPP intersection will be taken at the right hand side of the line x1 equals to 1. So this is again the unbounded feasible region of LPP3, and this case the optimal is turning out to be at this point. From B it has shifted to D, and the coordinates of D you can find by putting x1 equals to 1 in this equation. So you get z equals to 11.7. So we have got both the optimal solutions of LPP2 and LPP3, and both of them are non-integers. So that means the question has not finished yet. We need to do the further branching. So we need to do branching, but we need to decide that whether we should do branching at LPP2 first or we should be doing the branching at LPP3 first. So this is an important decision you have to make, because if you choose this step wisely, you will be saving a lot of your steps and iterations. So remember how to choose this. Okay, we are answering this, which node should be branched first. So in a maximization problem, you choose the node with larger z to branch first, and in a minimization problem, you choose the node with smaller z to branch first. So since here we are working on a minimization problem, so I am choosing the node with smaller z. So smaller z is z equals to 10. So this will be chosen for further branching. And why this is so? Why this rule is working? Because with branching, z has to increase in a minimization problem. So here z is already 11.7. If I'll do branching at LPP3, so the chances are I'll be getting z is 12, 13 or higher. But if I do branching at LPP2, then the chances are I may get z 10, 11 or even 12. So 11 is less than 12, so there is a possibility that this will give me a better solution. So I will be choosing this as branching node. So I'll be doing branching of LPP2 first. And since x1 is integer, so I have to choose x2 for branching, because you have to choose the branching variable, that one which is non-integer. So it's 2.5, so you'll get two branches less than equals to greater than equals to 3. So now you purely focus on feasible region of LPP2, which is just this line starting from point C going upwards. Don't look at the feasible solution of LPP3 because we are doing the sub branching of LPP2. So in this feasible region you have to add this constraint, x2 has to be less than equal to 2. So this point is already 2.5, x2 is 2.5 here. So when you draw the line x2 equals to 2, this line will be here, and since this is less than equals to, so that means region will be downwards, and you can clearly see the downward region below the line x2 equals to 2 has no intersection with the feasible region of LPP2 because that is starting from the point C upwards. So since there is no common region, this is infeasible. We call it LPP4, but the LPP4 is infeasible. So obviously when you get an infeasible node solution, so we cannot do further branching. So let's focus on other constraint, x2 greater than equals to 3. So x2 greater than equals to 3. So when you will be drawing the line x2 equals to 3, so the region has to be marked upwards and you have to see the intersection with feasible region of LPP2. So this was original feasible region. Above the line x2 equals to 3, your feasible region now will start from the point E upwards. So point E upwards the region starts. So obviously in the minimization problem, E is going to be the optimal solution. So which is an integer solution 0, 3, and this is the fathomed node. So here also no further branching needs to be done. Now you go back to LPP3. So you look at the LPP3Z, it is 11.7. So if I do further branching at LPP3, what Z I can get? I can get Z either 12 or I can get 13 or higher, but I cannot get less than 12. I cannot get 11 because it is already 11.7. So minimum value of Z which I can obtain with further branching is 12, but since I have already obtained 12 here, so therefore there is no benefit of the further branching. So I'll stop here and I'll fathom this node also because Z cannot be improved. So that's how you can save your steps. Otherwise, if you continue the branch process, then you will yourself figure out that there was no benefit in doing that. And once all the nodes are fathomed, we have to choose the integer solution. Which one is this? Declare that as the optimal solution. So that finishes our second example. So we need to take these remarks when to fathom a node in branch and bound. There are three possibilities. When the integer solution is obtained, then you stop. When the problem at a particular node is infeasible, just like the case we saw in this example, or when further branching cannot improve the value of Z. So if you take care of these three things, you will stop at appropriately, and then when you stop all the nodes, so out of all the available integer valued solutions, you pick up the best one as per your question. So that's about it. Branch and bound technique that finished